Now this is the more formal definition of a tensor transformation. We'll let x mu be transformed to x mu prime x. Now a tensor of type Rs transforms as such, as we've seen before with the previous one, where in the previous one this part was just ended up as the Kronecker delta. Now we take a rank 2 tensor given here, and this object exists independently of coordinates, and the metric tensor g mu nu, the definition of metric tensor is a smooth symmetric non-degenerate 0-2 tensor field given here. Now the space-time interval, which has signature here, which will be familiar if you've seen special relativity, as the Minkowski metric. Now the raising and lowering indices are here. So to raising indices we multiply through by the metric tensor, either the inverse or the regular metric tensor, which would either lower or raise an indices. Now this operation depends on geometry. In position dependent, is position dependent on curved space-time. Now why the partial derivatives fail? Well, we consider a vector field v mu of x, and the partial derivative of v nu under coordinate transformation. This gains extra terms and it fails to transform as a tensor. This failure reflects variations of basis vectors. And now the Levi-Civita connection and Christoffel symbols, the covariant derivative we can define as such. Now the metric compatibility and torsion-free conditions, we require these to be true. These uniquely determine the connection. Now the Christoffel symbols given here, they are not tensors. They are coordinate dependent and purely geometric. Now the physical interpretation of all this is that they encode how coordinate grids move, and inertial effects and apparent gravitational forces. Now the normal coordinates at any point P is 0, but with the partial derivative with respect to nu, if P does not equal 0, so curvature cannot be transformed away, because the essence of general relativity is that what is happening in nature is intrinsic to nature. It is the coordinates we use shall have no bearing on any physical phenomenon that takes place in the universe, because obviously the coordinates were invented by humans and physics was not. So curvature cannot be transformed away, because it's an embedded property of the universe. Now, a geodesic has extremal curves. A geodesic extremis is this given here. Now, if we apply the Euler-Lagrange equations, we get the geodesic equation, and this will be the derivation results. Now, the interpretation is that this is the straightest possible line, and there's no force acting, and gravity is absorbed into the geometry. Now, parallel transport, a vector v to the mu is parallel transported if this condition holds. Now, this defines internal frames and free-fall reference systems. Now, curvature as a failure of commutation. Now, we consider this. This defines the Riemann curvature tensor, which is given here. The Riemann curvature tensor has the properties that it's tensorial. It measures intrinsic curvature, and it is 0 in flat space-time. geodesic derivation equation and relative acceleration of nearby geodesics is given here. Now this is tidal gravity and is physically measurable curvature. Now the Rishi, tensor and scalar as contraction is given here. This is the tensor and the scalar is given here. These objects enter Einstein's field equations. Now the physical meaning of curvature. Parallel transport around a loop fails and geodesics converge or diverge. Volume elements distort. Gravity equals space-time curvature. Where this leads, Einstein's equation here, where energy is energy and momentum. Geometry is energy and momentum. And that's just a formal definition of our tensors and what we do with them. Please do like and subscribe.